Alright, today we're going to be going over all probability distributions along with what their formulas are and an example to go with them. The first probability distribution we're going over is the Bernoulli distribution. So this distribution is represented by one trial. So example of this is flipping a coin once. Anything that only happens one time. And the thing about the Bernoulli trial is it only has two outcomes, being success or failure. So for a coin example, if you had your heads as your success, there's only a heads or tails. There's nothing else that you could get. So the random variable x will show the number of successes. If x is 1, that means that the success occurred, and if x is equal to 0, that means that the fail occurred. So the probability function, which means the formula that you'd put your values into if you're looking to find the probability, is p to the power of x, p being your probability. So for a heads, or for flipping a coin, to get a heads, your probability would be 0.5. So that's what you would put into the p, along with x, which is just whatever your variable x you're looking for, whether it being one success or one failure, and then it's going to be 1 minus p to the power of 1 minus x. Now the expected value for this one is just p, the second moment is just p as well, and the variance is going to be p multiplied by 1 minus p. And then finally, the moment generating function is going to be m subscript x of t, which is equal to 1 minus p plus p e to the t. So the expected value is the expected amount that you're going to get. So for this one, because you're flipping a coin one time, this probability of success is still going to be your p. Same with the second moment, and your variance, which is just e of the x squared minus your expected value all squared. And the moment generating function I can make a different video on later to do the proof of all the distributions. So an example of the Bernoulli's distribution, again, is if you flipped a coin once, was the probability of getting heads. So the first thing you want to do is set up your different equations. So if we have our x is equal to 1, we're just going to have p. But if we're going to have our x is equal to 0, it's going to be 1 minus p. So if the coin is fair, our p will be equal to 0.5, which means that our p is equal to x is equal to 1, which if you put into the formula will get you 1/2 to the power of 1 multiplied by 1/2 to the power of 0, which just becomes 1, so it's just 1/2. Now next up, we're going to do the binomial distribution. So the binomial distribution is the exact same kind of steps as the Bernoulli distribution, except the only difference is instead of it only being one trial, it can be n amount of trials. So it's still only a success or failure, but this time you could flip a coin 100 times. And as well as your probability, you'll use the binomial distribution if your little n over big N is less than or equal to 0.05, your n being the number of times you do something, and your big N being your total population. But we'll go over that when we get to a different distribution. And same thing, except instead of x representing either 1 or 0, which is the number of successes, we're looking for the number of successes in n trials. So our x could be much larger than 1. So our formula for the probability mass function, the only difference is in front of our binomial distribution, which is the p to the x 1 minus p, we're going to have it to the power of n minus x rather than 1 minus x because we're counting up to n. And in front of it, we're going to have n choose x because if you flip a coin 5 times, the different variations of whenever you get the head will change your probability. And your expected value is np, your second moment is np times np minus p plus 1, and our variance is np times 1 minus p. So an example of this is if we're trying to get exactly 3 heads and 5 flips of a fair coin. So in this question, we have our n, which is our total number of flips. Our low n is our total population, which is 5. Our x, which is going to be equal to 3, which is the number of successes we're looking for. And since we're flipping a fair coin, our probability of success is going to be 0.5. Now, if you put this all into the equation, you get 5 choose 3 times 0.5 cubed multiplied by 1 minus 0.5 to the power of 5 minus 3. Now, next up, we have the Poisson distribution. So this distribution is different than the last two because the number of trials is not fixed. So for the Bernoulli distribution, we had it maxed as 1 trial. In the binomial distribution, we still had an n number of trials. This one is not like that. This one goes based off of lambda, which is the average number of times an event occurs in a period of time. For example, 5 cars per hour, or 10 text messages per minute, something like that. The way to set up this equation is very different than what we've had previously. We're going to have e to the negative lambda multiplied by lambda to the power of x, where x is just going to be 1, 0 up to n. And our expected value is lambda because that is what our average is, so it makes sense that that would be our expected. Our second moment is lambda squared plus lambda, and our variance is just lambda because, again, it's just e to the x squared minus e to the x all squared, which would cancel out the lambda squared, leaving you with just lambda, which is where the variance comes from. So the Poisson distribution approximates the binomial distribution when the number of trials of n is large, which is a standard of around greater than or equal to 50, and the value of lambda, which is in the binomial terms n multiplied by p, is small, being less than 7. When this happens, instead of using our probability function, it just becomes e to the negative 1 over x factorial. And the moment generating function is e to the power of lambda multiplied by e to the power of t minus 1. So an example for this is if a call center receives an average of 4 calls per hour, what's the probability of receiving exactly 6 calls an hour? So since we're looking for in terms of hours, we don't have to change it. But if it was in terms of 10 minutes, we'd have to divide the 4 by 6, since that would become our new average. But our lambda is going to be equal to 4 because that's the average in our time frame. X is equal to 6 because that's the outcome that we're looking for. So if we put it into our formula, we'll get e to the power of negative 4, which is our lambda, multiplied by 4 to the power of 6 divided by 6 factorial. Now if you plug that into your calculator, that will get you the probability. Now next up we have the hypergeometric distribution. So this distribution is the probability of x successes in n draws from a finite small population, which is where the binomial part came from, where our little n over big N has to be greater than or equal to 0.05, or in terms of binomial, it has to be less than 0.05. And also, this is the only distribution in this video that is without replacement, which means that all the variables are dependent on each other. This is because the probability changes with each draw, and the probability size is reduced. And our random variable x will represent the number of successes from n draws. So the probability function for this one is m choose x, which means that you're taking your total number of successes possible in the population, and you're choosing the number of successes that you want, and you're going to multiply it by the total population size minus the successes that the total number of successes that can happen, and it's going to be choose, and it's going to be the remainder, which is the number of draws minus the number of successes that we already took. So the whole numerator is just picking how many successes we want and how many decisions are left. And this is all going to be divided by our total population size. Choose the total number of draws, which gives you all the possibilities of the number of draws. So that's going to be our total possibility. Now our expected value is n to the m. N multiplied by big M divided by n. Our second moment is supposed to be n minus 1 in the numerator. And our variance is there, and our moment generating function is a lot larger than this one, but it's just a sum of all of our possible n's. But this time it's just to choose, because you take the divide out of the sum, and you have to multiply it by our normal moment generating of e to the tx. So our question for hypergeometric is, if we have a deck of 52 cards, what is the probability of drawing 4 aces and 5 draws without replacement? So because we see without replacement, that lets us know that we're using the hypergeometric, because that tells us that our variables are dependent on each other. So with our equation, we're going to try to find what all the variables mean. So our n is going to be our total population, which is the amount of cards we have in the deck, which is 52. Now our m is going to be equal to 4, which is the total number of successes in the population, because there's a total number of 4 aces that we could possibly get. Now our n, our little n, is going to be equal to the number of draws, which is 5, because we're drawing 5 cards. And finally, since we're looking for drawing 4 aces, our x is going to be 4, because that's the number of successes we're looking for. Now, in our equation, I just fixed it. It's 4 choose 4 multiplied by 52 minus 4 over 5 minus 4, and then 52 choose 5. Now our second last distribution is the geometric distribution. So this distribution is a little different, because instead of having a fixed number of successes and a fixed number of trials, we have a fixed number of successes. And this is because we're trying to find the first success in a sequence of independent trials, which just means that their probability doesn't change, because that would be a hypergeometric distribution. So like I said, the number of successes is fixed at 1, and our probability of success is denoted by p. So we're looking for the first success to occur on trial x, which means that x minus 1 failures must occur before the first success, because otherwise it wouldn't be the first success. And our random variable x is the number of trials that are required to get the first success. So our formula is going to look a lot like the Bernoulli distribution from the beginning of the video, but instead it's going to be 1 minus p to the x minus 1 this time, instead of 1 minus x, and it's going to be multiplied by just p to the power of nothing. And again, we have our expected, our second moment, and our variance there, along with our motion generating function. So the example of the geometric distribution is asking what the probability is that the first success occurs on the third trial in a series of Bernoulli trials with a success probability of 0.2. So our x is going to be 3, because that's when we're looking for our success to occur, and our probability is going to be 0.2. So putting that into our formula, it gets us 1 minus 0.2 to the power of 3 minus 1 multiplied by 0.2. And finally, we have our negative binomial distribution. This is the same thing as the geometric distribution we just did, but instead of our successes being fixed at 1, it's going to be our number of successes, again in a series of independent trials. So this means that we're just looking for when our number of success happens at x trial. So on our last question, we had trying to find our success to occur on our third trial. But this, with the negative binomial distribution, it could ask us to find when our fifth success is, and if we want to have our fifth success on our 9th trial, something like that, where there's more than one success occurring. The formula for this would be x minus 1, choose r minus 1, multiplied by the probability to the power of r, and then is 1 minus b to the x minus r. And our expectation is there, along with our second moment, our variance, and our moment generating. Now, the example for our binomial distribution is asking what the probability of having the third success on the 7th trial in a series where our probability is 0.4. So this one, because we want to have our third success, we know that our r is 3. Because our r is when we want the success, what number of success we want it to be. Our x is going to be 7 because that's the number of trial that we want it to be on, and our probability is 0.4 because that's just the probability of our statement. So putting it into the formula, it'll give us 7 minus 1, choose 3 minus 1, multiplied by 0.4 to the power of 3, and then multiplied by 1 minus 0.4 to the power of 7 minus 3. Now for our overall summary, we have our uniform distribution, which establishes equal likelihood, which would mean you just roll a die 6 times, or you roll a die 1 time, what's the probability of getting 6? It's just an easy 1 over 6. So our Bernoulli is our failure distribution or success distribution, which only has 1 trial. And it is a basic building block because, as you saw, a lot of the other distributions had a similar base to the Bernoulli. So next up is the binomial, which extends the Bernoulli to multiple trials, all with equal probability, and it's approximated by Poisson when n is large, which is greater than 50, and n multiplied by p, or lambda, is less than 7. Now the Poisson is the number of trials is not fixed, and we look for an average number of times that an event occurs. Hypergeometric is similar to binomial, but instead it will account for small population, and it will be without replacement, which, as you saw, is the only one that is without replacement. And then geometric focuses on the number of trials until the first success, and then the negative binomial extends the geometric to count until r successes in x trials.